All right. Okay. So this is actually a very classical topic in number theory because it relates to the distribution of prime factors. And this work was motivated by an observation I made in 2015, which was a variation of what has been happening in the subject for a long time as far as the distribution of number of prime factors is concerned. That's what prompted the study. So in order to even set up the problem for you, I need to give a background. But the background is an extremely interesting history. So it is independently of great interest. So I'll anyway do that. And then you'll understand why this particular problem has some interest in it. Now what happened? Oh, otherwise I have to move. Don't worry. I'm not able to move. I'll just not working. Oh,
let's do that.
Okay. I mean, it was working before.
Yeah.
I think they did something and it's not working.
Okay.
Yeah. There. Why is something working? I don't know why. Okay. All right. So we start with a fundamental observation of Hardy and Ramanujan going back to 1917. So they were interested in the phenomenon, round numbers are rare. And this is something that we have noticed. That's why when we get an answer which is a round number, we feel pleased because this is rare. So how do you define roundness? You can define roundness in two possible ways. By counting the number of prime factors and asking that quantity to be large, or you can count roundness by the number of divisors. But Hardy and Ramanujan arrived at came to the conclusion that roundness is best measured by the number of prime factors, and they said a number is round if it has a large number of relatively small prime factors. This is, of course, sort of an intuitive thing. So what we do is we take two measures of roundness. One is the number of distinct prime factors of n, which we denote by nu of n, and then the total number of prime factors of n, which we denote by capital omega of n. The first observation of Hardy and Ramanujan is that if you look at the average value of nu of n and omega n, they are both the same. They are log x on an interval from 1 to x. So it doesn't really matter whether you count prime factors distinctly or whether you count prime factors with multiplicity. As far as the average is concerned, a number has about log n prime factors on average. Doesn't matter which method of counting you choose. Are you okay with this volume? Okay. But now the point is this. The average in many number theoretic functions does not represent the most frequently occurring value. Sporadically large values tend to influence the average. So the question arises, is this log n that is the average value of the number of prime factors actually about the most commonly occurring value? So in that context, Hardy and Ramanujan define what is called a normal order. So an arithmetical function f of n has a monotone function g of n as its normal order if the ratio n epsilon of x divided by x tends to 1 as x tends to infinity, where n epsilon of x is the number of integers up to x for which that ratio f of n over g of n lies between 1 minus epsilon and 1 plus epsilon. So for every epsilon greater than 0, the probability that f of n over g of n lies between 1 minus epsilon and 1 plus epsilon is 1. Then you say that g of n is a normal order for f of n. Okay, so this is the idea of a normal order. And the second theorem of Hardy and Ramanujan is that both little omega of n and nu of n and capital omega and nu of n have normal order log n. That means almost always these are asymptotic to log n. So that means this is a good measure of what is really happening most of the time, and a good measure of roundness. Okay. Now, Hardy and Ramanujan had a brilliant idea of how to establish this normal order. So what they did was they looked at the local distribution, that is the number of integers up to x, which have a prescribed number of prime factors. So let me first look at the smaller of the distinct prime factors. Call that number nk of x. We'll come to nk star a bit later. So they showed uniformly that less than is the same as capital O. This is the Landau notation. Nk of x is of the order of magnitude not exceeding x over log x, log x plus some constant to the power k minus 1 over k minus 1 factorial. And they could actually establish this by induction on k. So this was not difficult at all to get this upper bound. Now, why does this upper bound work so well? Well, the reason this upper bound works so well is this is like a Poisson distribution. So what we are really looking at is, if you want the almost always size to be about log n, if you go to the Poisson distribution, c to the k over k factorial, the biggest value is around k equal to c, when c is large. Therefore, if you deviate from that largest value by a quantity c to the square root of half plus epsilon, that means you're looking at the tail of the Poisson distribution, you collect nothing. Everything is happening between c and c to the power half plus epsilon. Excuse me?
I will turn on the camera so that they can see you.
Okay. All right. So in the Poisson distribution, the main contribution comes from this peak c with a range of c to the half plus epsilon. So everything that occurs outside is negligible in terms of contribution. So it follows from the Hardy-Ramanujan upper bound that if you look at integers for which the number of prime factors, integers from 1 to x, for which the number of prime factors deviates from log x by a quantity more than log x to the half plus epsilon, the probability of such integers is 0. That means almost all integers will have the number of prime factors to be log x plus capital O of log x to the half plus epsilon. That proves the normal order. So it's very, very brilliant observation by Hardy and Ramanujan. Now, if you look at the total number of prime factors, it's a little bit complicated. You get a series like this, but you can still handle this series. And I don't want to get into the technicalities of handling this series, but there is a point that I will make later when I get to an observation of Selberg. Now, in 1934, Paul Turan, the Hungarian mathematician, gave an extremely elegant proof that the number of prime factors has normal order log n. So his observation was, just look at the number of prime factors, subtract log x, square it, and by just expansion. So if you square it by expansion, he was able to show by taking into account cancellations that this does not exceed x log x in size. So what does that mean? If you denote by n twiddle delta of x to be the number of integers up to x for which nu of n minus log x is greater than delta square root of log x, those integers are part of the full sum, right? But therefore, this is at least n delta of x times delta squared log x. But this is supposed to be no more than x log x by Turan's upper bound. Therefore, you get an upper bound for n delta of x, which is just x over delta squared, which means as delta goes to infinity, it's little o of x. This is insignificant in comparison with x. And Hardy and Ramanujan are really talking about delta being of the size of the square root of log x, and therefore this is a beautiful proof of this normal order observation of Hardy and Ramanujan, but by looking at the second moment. Okay, so that's the thing. Now, some years later, the Russian mathematician Probabilistic observed that this Turan inequality can actually be generalized to what are called additive functions. So these are functions, I'm taking here a strongly additive function which satisfy this property. The number of prime factors satisfy this property with f of p equal to 1. For such functions, Probabilistic noticed that the average is given by summation f of p over p, and the variance is given by summation f squared p over p. So the Turan-Probabilistic inequality is summation f of n minus a of x squared is less than xp of x. Now, if f of p is 1, this is the sum of the reciprocals of the primes, and that's the log x you see. The sum of the reciprocals of the primes diverges like log x, and this is again log x, and that's the log x that you see there. So this is the Turan-Probabilistic inequality valid uniformly. The implicit constant is uniform for all additive functions. So this is an extremely useful inequality due to covariance. Okay. Now, I want to say something about probabilistic number theory very quickly. This entire program was, this entire collection of observations was put in a grand setting with the Erdős-Katz theorem. So I'll tell you what the Erdős-Katz theorem is. You look at this additive function f(f). You have this a of x and b of x as is been defined before. And now you make two simple assumptions, that the value of the function on the primes is bounded, but the variance still goes to infinity as x goes to infinity. F squared p over p, like summation 1 over p diverges. Then this beautiful theorem of Erdős and Katz says, count the number of integers up to x for which f of n minus a of x is less than v square root of p of x. Divide by x, so that is the probability. Fxv is the probability function. Now let x tend to infinity. This tends to the area under the Gaussian curve minus infinity to v e to the minus u squared over 2 du, 1 over square root of pi. So this is sometimes called the central limit theorem in number theory. It's one of the most beautiful results. There's an interesting story of how this came about, and I'll just tell this to you in a minute. Mark Katz, the great probabilist, was giving a lecture at Princeton in 1939 on applications of probability to problems in analysis and number theory. So he mentioned a certain fact, which I'm going to tell you now, and Erdős was in the audience, and Erdős got up and said how Katz could complete the proof. So that's how this theorem was formed. So what is Katz's basic idea? His idea is define random variables, rows of p of n is 1 if p divides n, and 0 otherwise. So the probability of a randomly chosen number being a multiple of p is 1 over p. So the probability that this row of p equal to 1 is 1 over p. And the probability that it is not equal to 1 is 1 minus 1 over p. But the beauty is the probability of a randomly chosen number being a multiple of p is independent of the probability that it's a multiple of q, or nearly independent on an interval from 1 to x. So his comment was, these are random variables which are nearly independent. And therefore, this additive function should be thought of as summation f of p rho p of n in terms of this random variables. Therefore, his comment was, compare it with the sum f of p x of p, where these x of p's are truly independent random variables, not these nearly independent, but truly independent random variables, taking value 1 with probability 1 over p, 0 with probability 1 minus 1 over p, and then appeal to the central limit theorem to get some sort of a Gaussian result, but he was not entirely sure how to do this. So Erdős was listening to this lecture, got up and said, I know how to do this. This comes from Brun's sieve. So Erdős's comment was that he didn't know any probability. Mark Katz didn't know any number theory or sieves, but the two got together and proved this theorem. So his comment was that two brains are better than one. So Erdős believed in collaboration. Okay. So this theorem actually came about. But what was the thing that Katz was missing? Katz was missing an estimate for the following quantity. We all know that to get prime numbers, you start sieving. That is the sieve of Eratosthenes. But don't sieve all the way up to square root of x. Sieve all the way up to y, some point midway, y. And the number of uncancelled elements we'll call as phi of xy. So phi of xy, the number of uncancelled elements in the sieve of Eratosthenes, will be integers, all of whose prime factors will now be bigger than y, because you have eliminated all the numbers whose prime factors are smaller than y. Under probabilistic reasoning, the probability that a number is not a multiple of p is 1 minus 1 over p. So you should expect phi of xy to be of what size? Total number of integers is x. You've eliminated the multiples of 2, that's 1 minus half. You've eliminated the multiples of 3, which is 1 minus 1/3, dot, dot, dot. So the probability should be this. That should be the probability, and therefore this is the size of phi of xy that you expect. Unfortunately, this is not always true. This is true if you sieve up to a point y, which is like x to the epsilon goes to 0. So if you sieve up to square root of x, this estimate is wrong. If you sieve up to cube root of x, this estimate is wrong. But if you sieve up to an x to the epsilon, where epsilon goes to 0, this estimate is still correct. So what Erdős pointed out was, this theorem of Katz must first be established for an fy of n, not for f of n. You have established for an Fy of n where you truncate the number of prime factors of y, but y is x to the power of epsilon, but since the b of x tends to infinity, it is possible to choose this epsilon tending to 0 based upon the growth of b of x, and then by appeal to the Probabilistic inequality, he was able to close the gap between Fy and f and establish the theorem for all f. So this was the technical piece that Katz did not have. But Katz had the basic idea, the independent random variable. So this is how the Erdős-Katz theorem was proven. Now, once the Erdős-Katz theorem was proven, it was that was for the Gaussian distribution. Probabilius later got a theory of how to establish this for non-Gaussian distribution. That's the theorem up here, but I don't want to go into the theorem because it's not really needed for our particular program. The other question that arose was, since Turan was the second moment, is it possible to establish the Erdős-Katz theorem by the method of moments? That is, you calculate all the moments, and the moments coincide with the moments of the Gaussian distribution, then the original distribution must be Gaussian. The answer is yes, and that was subsequently done by Halberstam, but it was, the calculations were quite painstaking. All right, so that's the background. So I have Halberstam's theorem here by the method of moments. Now we move on. And then Elliott established this general inequality. We don't need all this for today's lecture. All right. Now, this is the theme that we are going to focus on. The great mathematician Edmund Landau, one of the authorities in prime number theory, said, once you have the prime number theorem, you can actually asymptotically estimate the number of integers with the prescribed number of prime factors as long as the prescribed number is fixed. So the prime number theorem tells you how many numbers have one prime factor. You might say, no, sir, what about p squared? Yeah, but the number of p squares is negligible, p squared, p cubed. So just focus on powers which are square free. The prime number theorem says the number of primes up to x is x over log x. How many integers have two prime factors? Well, Landau says, using the prime number theorem, it will be x over log x times log x. How many numbers will have three prime factors? X over log x times log x squared for 2 factorial. More generally, for each fixed k, Landau said that the number of integers up to x with the prescribed number of prime factors is x over log x to the k minus 1 over k minus 1 factorial. But this is for fixed k. Hardy and Ramanujan's bound is capital O, valid for all k. So there is a difference. For every k throughout, doesn't matter where k is, k varies with x, they had a bound. Whereas Landau said, if you fix the k, I can get an asymptotic estimate. Very good. Now Hardy asked the following question. Landau is able to get an asymptotic estimate for fixed k. Ramanujan and I are able to get a uniform upper bound for all k, regardless of whether k is varying with x or not. Is it really possible to obtain an asymptotic estimate for all k with k varying with x? So in other words, a Landau type result. So this was a famous problem of Hardy. Now this problem was actually solved by the Indian mathematician Sathe in 4 long papers. So here is Sathe's result. So Sathe said, this nk of x is exactly like the way Landau got it. This is for nk star for capital omega. So you got this log x to the k minus 1 over k minus 1 factorial. Then attached to it is a quantity which he called little g of k over log x and capital G of k over log x. So it all depends upon the relative size of k with log x. So if k is like 1/2 log x, then g of half is a constant. If k is like 1/3 log x, that ratio is 1/3, g of 1/3 is a constant, and so on. But the most interesting thing about Landau's result is g naught and capital G naught are both 1, which means if you put 1 here, this is the Landau result. If you chose fixed k, k is fixed and x tends to infinity, this is what the g naught is, that is the 0. And the most commonly occurring value, log x, right? We already know that almost all numbers have log x prime factor. If you go to the most commonly occurring value, this ratio is 1. And at 1, this g function again comes back and takes the value 1. So the g function fluctuates, starts at 1, fluctuates in between, and comes back to 1. The capital G function also starts at 1, fluctuates in between, and comes back at 1. And so Sathe established this result. Sathe established this by induction. And it was painstaking. Because, you know, it's induction on a K, and the K is varying with X, and you got to do all the error cuts. But he was brave enough. He finished the job and submitted 4 long papers. I don't know, it was like 100 pages or 120 pages, and he submitted it to the transactions of the AMS site. I told Hoffman that I'm going to tell a story, and so I'm going to tell the story. I hope he's still there. So he submitted it to the transactions of the AMS. But it turned out that the paper was sent to Atlas Selberg to referee. So Selberg looked at this paper of Sate and said, these are beautiful results, but this is really not the way to go about it. You got to do it analytically. And in 5 pages, he sketched an argument which gave all of Sate's results in stronger form. But it's also the way Selberg wrote. He wrote it in 5 pages. If you and I write the paper, it probably will be about 15 pages. Nevertheless, it was a referee's report, and he sent this back to the author. And then it turned out that, I don't know how this happened, this was published in the Indian Journal of the Indian Mathematical Society. And what they did was they published Sate's 4 papers, and side by side they put Selberg's 5-page referee's report as a regular paper by Selberg. So obviously Sate would not have been pleased. In the same journal, somebody else was saying this is a better way to do it. I actually asked Selberg at the Institute for Advanced Study what happened to Sate. And then Selberg was sitting looking over at the beautiful lawn, and he said, I think Sate took one look at my paper and decided not to do mathematics anymore. But that's it. After that, Sate did not do any mathematics. So I'm not going to tell you something about Selberg's work. So here is Selberg's idea, very beautiful. He takes a complex number Z and looks at summation Z to the power nu of n. You can also do Z to the power omega n. Z to the power nu of n is a number of prime factors. And now he says, by Cauchy's theorem, if I take this SZ of x, divide by Z to the k plus 1 dz and do a counter integral over a suitable contour, this should select the integers with a fixed number of prime factors with k. So this will give you n k of x. So there are 2 things in the Selberg approach. 1, estimate SZ of x asymptotically in the complex plane. 2, after you do that, choose a suitable contour to get nk of x. So these are the 2 principal ideas of Selberg. Okay, so now why did Selberg feel that this would be a good thing to estimate? Well, now look at the Riemann Zeta function. Riemann Zeta function, as we all know, has this nice product representation in real part that's bigger than 1. And now Selberg says that if you look at this Z to the nu n over n to the power s, that's the Dirichlet series product representation. But now that is Z over p to the s minus 1. So the principal contribution to this is coming near s equal to 1. So because that's the divergence of the prime. So if you go near s equal to 1, you can think of this as zeta s to the power z multiplied by the gs of z. Now zeta s to the power z is 1 minus 1 over p s to the power minus z. So it's that multiplied by the g, and that g function is this function. That's the g you see in the Sate formula. So he identified that in terms of what is coming out of this representation of the Dirichlet series in terms of zeta s to the z. Therefore, and then the other one is that for the capital omega, you get this capital Gs. Okay, I'm not getting into the details for capital omega. All right, so you got this. So now what is he going to do? So now what Selberg says is, keep that on the side. Consider this general generating function, zeta s to the z with this coefficient dc, and call this as the generalized divisor function. Why is this called the generalized divisor function? Because for the standard divisor function, this is zeta s squared. Generate the Dirichlet series for D of n, the number of divisors of n is zeta s squared. So the generalized divisor. So now he uses the well-known technique in analytic number theory that if you have a Dirichlet series, the sum of the coefficients of the Dirichlet series can be obtained as a Perron integral from a minus it to a plus it 1 over 2 pi I. Actually, it's a minus infinity to a plus I infinity. But then it's an exact formula, but usually you truncate it, and this is the error term. So in this case, all you have to do is to replace that general thing by the zeta s to the z. So this is the integral that you have to evaluate, and it's typical to choose a to be 1 plus 1 over log x. That's what you do in the prime number theorem. Good. But now, is there any complication arising here? Well, the complication is zeta s has a simple pole at s equal to 1, but zeta s to the power z has a branch point. Therefore, he has to use the Hankel contour for the gamma function. Right? I have a Hankel contour somewhere. I wrote it down here. There. So Selberg uses this Hankel contour for the gamma function and then shows that the asymptotic estimate for that sum is x over log x to the 1 minus z times the gamma function plus an error term which is like log x to the 2 minus z. So that is really the size. And therefore, if you now want to get to the size of this z to the number of prime factors, you've got to multiply this by the g function that Sate has. So this is the result that he gets for z to the number of prime factors, the corresponding result for the capital omega. Except for capital omega, the z has to be no bigger than 2 minus delta. Sate already noticed that in his asymptotic formula, he could not go beyond 2 log x. So Selberg explains why you can't go beyond 2 log x, because of the pole in this generating function 1 over 1 minus b to the s generated by the prime 2. So that is the reason why this happens. So he explained it analytically. But now, a very interesting thing happens. When he starts evaluating this contour integral, the appropriate radius of the contour turns out to be k minus 1 over log x. Very important why you choose k minus 1 instead of k, because what happens is when you choose k minus 1 over log x, there is a little trick that takes place. Okay? That little trick is that, I think I explained the trick to the next one. There is a certain integral that actually vanishes. Okay? And because that integral vanishes for this particular choice, Selberg is able to get a uniform error term of 1 over log x squared compared to this. Here it is k log x to the k minus 1 factorial times this. But the relative error is k over log x squared. That is extremely important because the most commonly occurring value of k is log x. So you want to take k as big as log x or 3 log x or 4 log x, which means the denominator of this relative error has to be bigger than log x, and Selberg was able to achieve the log x squared. So not only was Selberg simultaneously able to obtain the Sate result, he was also able to obtain the sharper error term by this analytic approach. So Selberg, and that is the reason why the editors of the journal decided, even though this is a referee's report, this has to be published as a paper, because this has pointed out to a very important method in analytic number theory, but sort of, it's a slap to Sate, but was a benefit to the mathematical community. So they made that decision. Okay, so this is, so Hardy's problem was solved by both Sate and Selberg. But Selberg in his paper says Sate's results are very beautiful. To get a praise from Selberg is not easy. It's not at all easy. All right, so that's that. Now I'm going to say something about some work that I have done in the late 70s, which is related to this current breaker. All right, so we talked about the number of uncancelled elements in the Selberg-Eratosthenes phi of xy. So let me say something a little bit more detailed. I said you get this problem, this asymptotic estimate x times the product, but it doesn't work beyond. So the question you have to ask is, what works beyond? So let us write down phi of xy is the number of uncancelled elements in the Selberg-Eratosthenes. S of xy is the set of uncancelled elements in the Selberg-Eratosthenes. There is a fundamental identity that this phi of xy function satisfies. The fundamental identity is phi of xy is phi of xy to the h plus summation phi of x over pp, but the primes range over y to the h. This can be proved combinatorially. It's not a very difficult thing to prove. Now, what does this actually achieve? What this actually achieves is, if you denote the ratio of log x over log y by alpha, that means y is x to the 1 over alpha. This permits evaluation of phi of xy by induction on integral part of alpha. So let me just explain this in a very simple way. If you swim all the way up to square root of x, you're only left with primes. And the number of primes is x over log x. So you have an asymptotic estimate for phi of xy all the way up to square root of x. Even you can go a little bit beyond. Even if you go up to x to the, little bit beyond square root of x, you will still have x over log x. So in terms of alpha, The prime number theorem is giving you an estimate in the interval 1 to 2 for the value of alpha. Now you use the bootstrap identity. Choose y to the h to be square root of x, and then y is, let us say, between square root of x and 2 root of x. Then this ratio gives you a log value, which is log x over log p divided by log p, which means log x minus log p over log p, which is log x over log p minus 1. That means it's a shift of the interval by 1 unit. Therefore, knowing the value in the interval 1 to 2 permits you to calculate in 2 to 3. That permits you to calculate 3 to 4, and so on. So this phi of xy can be calculated inductively by induction on the integral part of alpha. So what it leads to is, it actually tells you that phi of xy is of the order of magnitude x w alpha over log y. Forget about all this, where the w satisfies a difference differential equation. So this is wonderful. So this, when I give these talks to a mixed audience, on the one hand, they see complex variable theory coming in. On the other hand, they actually see differential equations coming in. So this w alpha is a function which satisfies a difference differential equation. If you analyze this difference differential equation a little bit closely, you will see that as alpha tends to infinity, this function tends to a constant. Now the question is, what is that constant? The constant tends to be e to the minus gamma. This is the famous Merton's constant, because e to the minus gamma, it comes in the asymptotic estimate product 1 minus 1 over p. P less than y is asymptotic to e to the minus gamma over log y. So that is where the e to the minus gamma is coming from. And it approaches this limit quite rapidly because its derivative is actually going to 0 faster than, like I put this here as alpha log alpha, but it's actually minus alpha log alpha minus alpha log log alpha. It goes to 0 faster than the reciprocal of the gamma function. 1 over gamma z goes to 0 like e to the minus z log z. This is going to 0 faster than that. All right, so this is the background on the phi of xy. All right, so having said that, so this is a famous paper of De Bruyne, this Dutch mathematician. The number of uncancelled elements in the Selberg cluster is Proceedings in the Netherlands Academy 1950. Okay, now let me come to a problem that I was interested in back in the 70s. So this is related to my PhD thesis. So one of the questions I asked myself is, we have the Irish-Gas theorem. In the proof of the Irish-Gas theorem, we use phi of xy. But why is it nothing is known about the distribution of the number of prime factors among the members in the Selberg Eratosthenes? So in other words, among the uncancelled elements of the Selberg Eratosthenes. So my problem was, look at phi of xy, look at that set. What is the distribution of the number of prime factors in that set S of xy? This is a natural question to ask, and very interesting, because initially you have prime, then you have 2 prime factors, then you have mixture of 2 and 3 and so on. What is the actual distribution of the number of prime factors? That's the question I asked. Now, by that time, I had read Selberg's paper, so I decided not to do this by the Zeta method, and thereby obtain beautiful result, but stop doing research after that because all energy is break down, but instead follow the Selberg method. So the final result I got was something very nice. Phi lambda of xy is the number of integers in the among the uncancelled elements, such that the number of prime factors minus log alpha. So log y, log x is now replaced by log alpha, which is log x minus log y, is less than lambda square root of alpha, log alpha. Then the probability tends to the Gaussian limit. Not only that, the uniform error term 1 over square root of log alpha. So this is absolutely uniform in all of y and all of x. So this is the result that appeared in the Quarterly Journal of Mathematics, and I didn't expect this, but it turned out that the implicit constant is actually absolute. But now I just one word as to how this was achieved, because that method is used later in my current work. So the way this method was achieved was, yes, I look at this sum, which is now the analog of the Selberg sum. And naturally, after this, I can do a contour integral, divide by z to the k plus 1 to get the local distribution. And from the local distribution, we can get the global distribution because we know Poisson tends to Gaussian, right? So if you prove asymptotically that locally it's Poisson, then the Poisson will tend to Gaussian. So this is the result that we got. So essentially what I had to do was divide the range into so-called small values of y and large values of y. If y is small, it turns out that the generating function approach of Selberg works. What do I mean by small? E to the power, there should be an x here, log x to the 2/5. That's a small, possible small value, okay? So e to the power log x to the 2/5, in that range. Whatever Selberg did works. So I've written down here the Selberg type of result, but now it's GY1, GYZ, G1Z, I don't have GYZ. And I've given you the generating function for GSYZ here. So this is the analog of the Selberg result, valid for small values of y. And the method is the same. I go through the Selberg. So I'm not going to tell you that the contour integral, it's one last sentence. What about the large values? How I learned from De Bruijn. De Bruijn says for large values of y, start with primes in square root of, when you sum up the square root of, from between square root of x and x, use Buchstabe, go to cube root, go to the 4th root, go to the 5th root. So I start from the top and come to the bottom. So is a Buchstabe identity possible? Yeah, the answer is yes. This sum SZXY, like the sum phi of xy, satisfies a Buchstabe identity, except now there is a parameter z. When z equal to 1, this is the classical sum phi of xy. So again, I can do estimation by the induction on integral part of alpha. I go through the details. But now I get a function which satisfies a differential equation analogous to what we had before. But now I have a z here. Formerly I had a 1. So I looked at this and I said, the method that De Bruijn had for phi of xy will now work for this function s sub z of xy. But of course, I have to do this with complex variable z. So I went through this whole process, and actually I got a continuous approximation to this quantity that satisfied an integral equation analogous to this Buchstabe identity. So the Buchstabe identity is a sum, whereas this is an integral. So this is the continuous analog to that. Now, they ask, why is this important? The number of primes of 2x pi of x is the discrete quantity, or psi of x, the sum of the logarithm of p of 2x. The continuous version is the logarithmic integral of x. So, the prime number theorem is the replacement of your pi of x by a continuous function, logarithmic integral of x. The logarithmic integral of x you can integrate by parts. Therefore, you get x over log x over log x squared 2 factorial, x over log x cubed 3 factorial, and so on. So you can approximate pi of x to as strong an estimate of 2x over an arbitrary power of log x as you need. So I have this quantity az xy, and I prove this theorem. And the beauty is I can now do the expansion using integration by parts. When I do the expansion by integration by parts, exactly as the prime number theorem, I get x over log y with this function, x over log squared y with the derivative, x over log cubed y with the second derivative, and so on. And therefore, it is a beautiful model analogous to the prime number theorem. However, this is for the uncancelled elements of the silver metaposthumus, which is more general. Prime number theorem is when you go all the way to the square root of x, what you're left with. So, but now there's one problem. What is the behavior of mz of alpha as alpha tends to infinity? f1 of alpha is w alpha, that previous function which tended to e to the minus gamma. Does this function also tend to limit? What happens? So if you normally want to deal with differential equations, there are various techniques. You form what is called an adjoint equation, and then you form an inner product between the two, and you start working with that. Or you represent the function as a Laplace integral, and then do a saddle point analysis and try to obtain an asymptotic estimate for the behavior as alpha goes to infinity. But still, it's fairly hard analytic calculations. But I wanted to avoid that. So here's the way I avoid it. I have an estimate by the Selberg method here for small y, starting from 0 or from 2 up to e to the log x to the 2/5. I also have an estimate for large y descending from the top by the Buchstabe method. Question. Do do the ranges for the large y and the small y overlap? The answer is yes. The range for the large y is this. Fortunately, e to the log x cubed is much less compared to e to the log x to the 250 power. The two ranges overlap. So I took a common point between the two ranges to get an actual asymptotic estimate for mz alpha, and we were able to show that mz alpha indeed approaches a certain limit. So the two ranges overlap. So that's what I'm saying here. And therefore, mz alpha is, this is the general result, e to the minus gamma z alpha to z minus 1. So I was able to solve this problem. Once I had this problem, I was able to do the Selberg results. So that is on one side. Now, I'm going to skip several slides now because, not only because of lack of time, but also because it's not entirely needed for this. But I'll just make one comment. There is a dual problem. I was looking at the Silver-Eratosthenes, where I'm looking at integers, all of whose prime factors are large. What if you look at prime factors, numbers, all of whose prime factors are small? Those are called smooth numbers. They are numbers, all of whose prime factors are small, and the function is psi of xy is the count of the number of integers up to x, all of whose prime factors are small. They are also a bootstrap type identity thing. De Bruijn was the one who studied this in great detail. And subsequently, the range of asymptotics was extended by him. I don't want to say too much. I first established a Probabilistic type inequality for integers which are smooth, which appeared in this journal. And subsequently, I was able to get an Erdős-Kac theorem for integers without large prime factors, simply with small prime factors. But the analysis here was much deeper. I really had to go through the full strength of the theory of differential equations with Volterra kernels and saddle point analysis by choosing contours and so on. So it's a fairly long paper in Acta Arithmetica, but I was able to establish an Erdős-Kac theorem in the dual case as well. Okay, so but I'm not getting into the details for this lecture. So now I'll come to the problem. So here are some key references: the work of De Bruijn, Hildebrand, and others over a period of starting from 50 and going up to the 80s. Okay. Now I come to the current problem where I talk about the variation of the classical theme, and I'll finish it in about 15 minutes. Okay, so now we are looking at the number of small prime factors of a number. So I just denoted by nu sub y of n. Small doesn't mean small. Small means small in comparison with x. X is going to infinity, and in this interval from 1 to x, so y could be anywhere. It could be a square root of x, or it could be e to the root log x, or whatever. So it's a truncation of 1. That's what I mean by small. Now, the problem I was interested in is how many integers are there up to x with a prescribed number of small prime factors? The Erdős-Kac theorem made fundamental use of nu yn. But the Erdős-Kac theorem is a global distribution. So I looked into the literature, and nobody had actually seriously studied the local distribution of the number of small prime factors. So I said, this is an interesting problem. It is a blend of the Hardy problem, the Hardy-Ramanujan problem, the Selberg problems, and the Erdős nu event that comes in the Erdős-Kac theorem. So let us do a serious study of this. But if everything is going to look analogous to whatever happened in the classical, then people are going to say all you did was you took the generalization, but the model is exactly the same. You're not getting anything new or different. Here, a variation takes place. That's the variation I want to talk about. It's a variation, but it's also, there is a similarity. So I now follow Selberg. I consider this sum S hat z of xy, which is this complex function z to the sum. Then I have to do it over a contour. So this is the general Selberg idea. Good. But now, again, the beauty here is this also satisfies when I put S naught, that's the number of uncancelled elements in this Eratosthenes. When I put z equal to, when I put y equal to x, this is the classical Selberg sum. So what I liked about this problem is two extreme special cases are well-established classical cases. So I'm really looking at a natural generalization of this classical problem. Now, actually, the case z equal to 1 was studied by a student of mine in a thesis, but it's not needed for the current plot, but I just mentioned it. It's in 1992. So now let me begin by giving you a feel as to why there is a variation. Okay, I'll do that very quickly. Start with n naught of xy. Let's understand what n naught of xy is. Now, n naught of xy means the number of integers up to x when nu y of n is 0. Nu y of n is 0 means it has no prime factors up to y. So all prime factors are bigger than y, which means it is the same as t of xy. So now what I do is to get a feel for this problem, I say, let us start with a very large y. Large means the y which is of the size of x, 1/3 x, 1/10 x, 1 over 1,000 x, whatever. Okay. So I did the ratio between x and y is fixed. We call that ratio beta. So let's look at it. Since y is constant times x, y is bigger than square root of x when x is large. Therefore, the only numbers remaining are the prime numbers between x and y. How many numbers, prime numbers are there between x and y? There are x over log x primes up to x. There are y over log y primes up to y. Subtract, and this is the arrow term. And now since y is x over beta, this is about the size x over log y times 1 minus 1 over beta. Listen, I said, my God, this is much bigger than what Landau had. Landau will say, the number of integers up to x, which have 0 prime factors, is 1. Every other number has a prime factor. So the only number which has no prime factors is the number 1. So the number of integers is 1 according to Landau. I get this size. So straight away, the problem is very different, looks very different from Landau. So let's look at n1 next one. That's where the problem becomes interesting. n1 xy means the number of integers up to x such that between 2 and y, there's only 1 prime factor. So those numbers are of the form a prime power multiplied by anything that occurs on the right which has got large prime factors. So call this number q. Now forget about q squared and so on, because they don't really contribute. It's only the single powers of factors. So it should be of the form q times m, where m is counted by the uncancelled elements of the circle and is actually q. So it should have all prime factors bigger than 1. So when I do this estimate, it turns out that I get x over log y times 1 over beta coming from this y, all primes of y. And there is this sum, 1 over q. Don't worry about that. 1 over q, q less than beta. This is what is happening. This is the Landau term. If you ask Landau, how many integers do you have up to x with 1 prime factor? He'll say, number of primes up to x is x over log x. That's Landau. Now, this is the new term that I get. What happens to this new term? It is the sum of the reciprocals of the primes up to beta. So beta is 5. The sum of the reciprocals of the primes up to beta is 1/2 plus 1/3 plus 1/5. It is just a small quantity. So these two are the same size. Beta keeps increasing. 20, 50, 200,000. This is a divergent series. This divergence like log beta. But this eats the value of this. So the Landau term shrinks and my term increases. So when you put x equal y equal to square root of x, this beta is of the size square root of x. Log square root of x is of size log x. What does that mean? That means n1 of xy is of the size x over log y times log y. If I choose y equal to x to 1 over alpha. I said, wait a minute. What is going on here? Landau, so if I take 0, Landau will say 1. I say x over log x. If I take k equal to 1, Landau will say x over log x, but I say x over log x times 1 log x. But Landau would say x over log x is for k equal to 2. So when you put k equal to 2, Landau would say x over log x. I now say x over log x squared over 2 factorial. This became very interesting. It is like Landau, but it is shifted. So I went through this process in 2015 to get some calculation. For nk of xy, I ended up with x over log y, log x to the k over k factorial multiplied by this W alpha, which is the bootstrap thing, came back into the picture. This is for 1 to the square root of x. So this is very interesting. Landau will give you, sorry. Oops. Why did I lose this? Okay, now I'll move this forward. Sorry about this. We'll get to it quickly. Yes. So Landau, for nk, you didn't have the y, he will give you x over log x with k minus 1 over k minus 1 factorial. Only at the level k plus 1 will he give you k and k factorial. So what is happening is, my thing is like Landau, but it is shifted by 1. But if it is shifted by 1, when k is fixed and small, I have an extra factor of log y. So mine is bigger than Landau. But when k is large, much bigger than log y, Landau is bigger because he has got a k factorial at the bottom. So it's a win, you win at the beginning and then later you lose. So in whatever reason, this is exactly what I got. And I give this as a problem to a PhD student, and I said, listen, I'm not making this initial study. I want you to actually go through the grind of the Selberg theory here and do this bootstrap differential equation and then do this asymptotic uniform. So that was his PhD thesis, but I had to work rather closely with him. So we wrote this giant paper. So now, so I call it the hair of the tortoise phenomenon. The hair of the tortoise phenomenon is, in the beginning, when beta is very close to, when y is very close to x, there is the divergence of the primes doesn't come in. The Landau term dominates. So that's like the hair. Then as beta starts growing, primes, reciprocals, and so on, they diverge slowly, but surely. So as soon as you hit x to the square root of x, my term dominates. So the tortoise wins the race. So that's why I call it the hair of the tortoise. So we also can, so this is the analysis by the Selberg method. So the generating function for the z to the 2y of n is given here. Okay, I go through this contour, but I don't need a Hankel contour because I just have the ordinary zeta function. I don't have zeta raised to the z. So when I go through that, I have to get an estimate, and the estimate that I get is this function, which I call L of z. There is a representation for L of z that I actually end up getting. All right, so we have that. Now the next thing is we calculate this nk of xy using this with an L of z. But now, interestingly, if I want to apply the Selberg trick, my radius of my contour is now k over log y. I do the calculation, and not k minus 1 over log y. Landau had k minus 1 over log y. I have k over log y. So that's again the difference. But when you do that, it looks like a small difference. When you do that, you end up with this main term, and like Selberg, you end up with this very nice error term, which means I can now solve this problem as k varies with the number of prime factors varies. So this problem, but this is not still a complete solution. This is only a solution when y is small. So what do you do when y is large? When y is large, we use the bootstrap method. And De Bruyne has told us about the phi xy. And this again satisfies the bootstrap identity. I can induct on the integral part of alpha. So when I do that, I end up with a function which satisfies a differential equation. We call this function m hat z of alpha. And then this m hat z of alpha has some specific form. I have to actually go through I'm sparing you the details of the calculation. And then we end up with something very similar, but the Selberg factor shows up. But what is important here is that this function, this as you go to infinity, diverges, this diverges at 1, the real part z is less than 0. So we first focus on real part z bigger than 0. And we go through this iteration process on the bookstop. The details are somewhat difficult, so I'm sparing you the details. But the point is, at the very end, we end up with an estimate, but now we have a function which satisfies a differential equation. So the question is, how do you deal with this function that satisfies a differential equation in terms of its limits? Oh, my thesis PhD student, do not worry. Do the estimate for the large y in such a way that the ranges overlap. So you will be spared this theory of differential equations and adjoints and so on. Make a comparison of the two with the range in between, and you should be able to get the limit. That came because it worked in my quadrature way. So we did that, and we were able to show that it approaches a limit L of z. And I'm going to tell you what L of z is. It has got a very nice shape. Given L of z somewhere. There it is. So the value of L of z is given here, and you see how beautifully Euler's constant comes. So when z equal to 0, you get that e to the minus gamma. That's what you saw in the phi of xy. So this is exactly what the L of z is. And so the problem of asymptotic estimate was solved. But now, finally, I have to do the contour integral. When I do the contour integral, I find that once again for large y, the ideal radius is k over log y, and not k minus 1. So the method works also for the large values. But now I have to mention one thing. When we did the problem, we had at that time no asymptotic estimate for real part of z less than 0. The current world expert on problems involving restricted prime factors is the French mathematician Jalal Tenenbaum. So back in 2015, I had told him about this problem. He said, we called it the Alladi variation of Landau's problem. So he worked on it. Though he didn't have these results, he had other results. And then he actually was able to estimate SZ of xy for real part z less than 0. But later we noticed that we only need our bounds, not asymptotic estimates in that region, because the real contribution when you do this contour integral is really coming from z equal to 1. So it's only on the right half we really need accurate estimates. As long as we have satisfactory bounds on the left, it's okay. So whatever be the reason, this problem was completely settled, and this long paper is appeared in the Additive Convolution profiles and so on. And so this paper of ours appeared in the Riemannian journal. The reason it appeared in the Riemannian journal is Tenenbaum wanted this paper in the Riemannian journal. And so we decided that our paper, Tenenbaum's paper, will appear side by side. But both papers are important. Tenenbaum's paper does not diminish the quality of ours, but it's a different approach. But our paper deals with the local distribution and somewhat relates with it. So that is really the story. So all this happened in 2018. So I'm presenting you something which is not a 2022 result, but a 2018 result. But I thought I would take you on this little tour, this excursion, starting with Hadi Ramanujan and coming to the present. Thank you.
Thank you. Any questions?
So I don't know whether Jerome heard my story on Selberg.
Yes, he did.
He probably did. He did. Okay.
Yes. Just one question.
Okay, wait a minute. Me?
Can you hear me?
Yes.
Yes, please. Now we can hear you.
Yeah. Now, Selberg's method applied to the Riemann Zeta function. Yes?
Yes.
Now, what happens if you replace the Riemann Zeta function by a Dedekind Zeta function?
Well,
is that a trivial question? Maybe you get the same thing, but nothing really new.
Right. You can replace that Riemann Zeta function by other functions, Selberg's method basically says that if it turns out that the Zeta power is this branch point, has this branch point, then you use this Hankel contour to evaluate the main contribution at 1. So it'll work. It has been used in other situations as well.
Well, then my other question is, the world is filled with all kinds of interesting Dirichlet series.
Correct.
For instance, L functions that come from modular forms.
Yes.
What happens if you try to apply this method?
So you can actually use L functions. There is absolutely no problem with it. The interesting L functions will be, the ones that will contribute will be the L functions which will have a pole at s equal to 1, not the L functions which will be analytic at s equal to 1.
Well, that's too bad, because modular forms, you expect them to be entire.
I understand that. For this method to apply. See, that is why, for example, when you do the prime number theorem for arithmetic progressions, you have different characters. Each character generates an L function, right? Only the principal character has this L function which has got a pole at s equal to 1. The other characters do not. So that is why you get this factor of 1 over phi of k, because it is only one out of these phi of k that contribute by this method. But I'm sure that there are other ways of dealing with coefficients of cusp forms and so on, but not by this particular method of Selberg. I mean, Selberg also has worked on modular forms.
Yeah, well, the other case would be Eisenstein series, and they do have poles. Their L functions do have poles.
Correct. Correct.
So this is just a very ignorant question, since I don't work in this. It's just curious. If I suppose people have, and Selberg himself perhaps has.
And some of the others who have worked at the interface between modular functions and classical analytic number theory would be people like Ivanets.
Yes.
He has papers dealing with sharp estimates and so on, and various others.
Right, even Serre.
Yes.
Well, thank you for your talk.
Welcome.
Any other questions?
I'm just wondering, how do you get the sense?
How do I get?
Get the sense of which question, which just
Yeah. So if you work in analytic number theory, you're doing estimates all the time. You get a good feel as to what will make the major contributions, where the contributions can be ignored.
so you don't have to compute. You don't have to count.
Well, I did some computation. That's why I did the simple computation for k equal to 1, k equal to 2, and so on to get a feel. But afterwards, you do the analytic approach. You're guided by these basic computations to help you decide what the nature of the contour should be. So, one must have some sort of a feel for asymptotic sizes to work in analytic number theory. This is there. And so I worked in analytic number theory for a decent time to get this feel.
That's the most difficult part.
Yeah, you first have to have the feeling, and then you need to really get into the trenches and start doing all these estimates. The important thing about the estimates are the error terms. I mean, I focus on the main terms for you, but I actually spend a lot of time controlling the error terms. The error terms can blow up. So that's analytic number theory is all about controlling error terms. It's hard analysis. But I thought this gives you a picture of the landscape, how Landau's problem came. It's a variation, but there is a similarity. Thank you.